So some of the common questions that I always get from the users and also some of the potential users are such as, can you model monolithic reinforced concrete structures and how? How do you model wing walls and walls at angles? Those the walls that are not perpendicular to the rest of the structure. How do you model the arched cover, the arched slab portion for the frame bridges or the culvert bridges? How do you reflect the soil property? How do you apply soil springs and loadings? How do you apply trapezoidal prismatic loadings? And how do you obtain the moment frame for the 3D model? And also, if you could design or rate the culvert structures using Midas Civil. And those questions can be segmented into 3 portions, modeling, analysis, and design. And based on the questions, the commonly asked questions, I actually outlined today's training as shown over here. So first, I'll be going over the modeling. I'll be first showing you how you can model using our reinforced concrete structure wizard. And then following, I'll be covering how you could actually manually model or modify. And then going into the analysis, I'll be showing you the regular ways of reviewing your result, just like the types that you know, diagrams, tables, and so on. And then the second portion is a little more special. So if you have a 3D model, how do you actually convert your values into the bending envelope moment diagram, which has to be done manually if you use just a regular typical 3D FEA program. So I'll use what are the features in Midas Civil that actually do that for you internally. And then design portion. So design can be done using the 2D modeling approach. So that will be the overview of the training. For the users and non-users, the program requirement is as shown over here. So for the version of the program, for the modeling and analysis portion only, any version of Civil can be used. The reinforced concrete wizard has been implemented from more than, it was one of the very first wizards that we implemented. However, for design check, you will need a recent version of Midas Civil, Midas Civil 2014 version 2.1 or higher. Doesn't matter if you have a conventional type of license or advanced type of license. Reinforced concrete structure is the conventional type, so both types can cover whatever that I covered in today's training. And no additional module is required for this type of application. So going into the actual modeling, so part A, the wizard modeling portion. So normal type of frame, underground frame, or pie type of frame, and box culvert, they can be all modeled using the wizard. And all of the structures can be modeled in 2D and 3D format. So based on the wizard, you will be able to create all different type of frame, culvert, and pie type reinforced concrete structures. And some of the examples are as shown over here. I'll be showing you how to model each them. And going into one of the questions asked, so one of the commonly asked questions are such as, how do you actually model the wing walls? And I'm going to show you 2 approaches. One by using the wizard. As you can tell, in the wizard interface, there is a part that you can define the wall portion. And then the second approach that I'll be covering a little later is the manual approach. So now let me open up the program and actually show you in the demonstrations. Okay. So I just open, this is a model file without any data, except I defined one single material, concrete, grade C4000, C4000. So anything I define in Midas Civil, you can actually review under the Workstream menu. So you can think of the worktree as like the backbone of the program. And as you can tell, under one single menu properties, material, and grade C4500 is defined for this demonstration. So the wizard can be found under the structure main menu. Under the structure menu, you can find a group of every single wizards Midas Civil provides you. And the reinforced concrete frame and the box type of structure that I'll be covering today is located right here. And from the interface, you'll be able to tell that you can define either two-dimensional or three-dimensional model. You can define normal type of frame structure, pie type of frame structure, and also the box culvert type of structure. So when you open the wizard, one thing you're going to notice is that by default, it's going to have certain values. So when you click around different part of the functions, you're going to notice that some of the interface kind of grays out because you're no longer going to need all of the data depending on the type of structure. And also second thing, you're going to notice that there are some of the values entered by default. So even if you're not familiar with the program, you can actually quickly open the wizard. And if you want to just see what the wizard could do for you, just simply test it out by saying OK. Oh. Give me 1 second. Okay, I apologize. I had some problem with my program, but here we go. So if you want to quickly test out the wizard, what you can do is choose the desired type of the structure you want to model. If you want to change around some of the dimensions, you can change them too. And when you hit OK, it's going to create a model with some of the default values that are already put into the wizard. So even if you're new to the wizard and this part of the program, if you want to quickly test it out, feel free to go ahead with some of the default settings. So for going over the wizard, I'll be showing you two examples. I'll be modeling just a frame type in 3D and 2D, and also I'll quickly show how you can model the box culvert in 3D. But a lot of things will be very similar to each other. So in detail, I'll be going over the interface just once with the box culvert example. So when you look at the wizard, you're going to notice there are 3 tabs total: longitudinal, transverse, and loads. And under the longitudinal, literally you could define the longitudinal basic informations. In the transverse, you'll be defining the transverse information. Loadings, this is where the program is going to control what type of loading you like to apply. Is there pavement and also soil information, any surcharge, underground water, what is the if there's topsoil on top of the slab, what is the depth of the soil, and so on. Those type of information will be entered under the loadings, which makes the wizard capable of considering the soil above and surrounding the structure. So going in detail for each tab, in the longitudinal main menu, you're going to see the main overview of the structure. And as you can tell, all the dimensions that you're about to enter, you can actually refer to the terminologies and what are its symbols implying and indicating. You can refer to this main picture. So going down one by one, we are going to model 3D dimensional box Culvert in detail. For the material, you can choose a material that you want to apply for the entire structure. So this way, you're reflecting it's a monolithic structure. And if you do not have a material that you want to apply over here, you don't have to close and go back to the properties to define the main menu. You can just click this dot 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 button right here and go to this properties interface in which you can define additional material or modify what you have already, or delete or just modify your material data in total. The size of the plate element, so for the three-dimensional structure type, the program is going to mesh your structure. And you have to, this is where you determine the approximate size of the mesh for the model overall. It's not going to be uniformly 3 by 3, but this is the reference that the wizard will be considering for the conventional size of plate element for the model that you will create. And depending on the complexity, you might want to reduce the size of the plate element. Or if the condition is very simple, if the analysis accuracy doesn't, if it doesn't have to be too complicated, you can stay with what the wizard kind of provides you by default. Span information and wing wall, what is the thickness of the wing wall, and skew angle, and also if the culvert itself is curved, you can actually click on the radius option and provide a curvature and the type of the curve like this. But today we'll stay with a simple, straight, and non-skewed structure. Dimensions, so I won't cover this in detail. It's a wizard and very straightforward. You could actually refer to the picture and the value one by one and actually shape the desired dimension that you need for the structure that you're working with. Now moving on to the transverse portion. Oh, but I want to mention one more thing. So if the structure is actually underground, if the top portion is simply a slab and just it's at the ground level, you don't have to worry about H2 or P. But if that's not the case, if the structure is actually underground structure buried under some soil, H2 and P will be where you reflect the depth of the soil. Okay. Moving on to the transverse tab. You can choose the type of the barrier setting, type 1, type 2, and type 3. And you can define the dimensions for those barrier structures. And I'm just going to assume that there's no additional loadings on the B4 area here. And this is for the pi frame structure, so it's grayed out. And the support of culvert, so you can actually define if it's going to be the general spring for the culvert, and then you can define the modulus of subgrade reaction and the length of the elastic link in order to reflect the soil property for the culvert on the culvert structure. This will make more sense when I actually show the model generated and when we review the model generated together. So let's hold on to that. Moving on to the loading, you can choose the load combination type, what type of load combination that you will have the program generate, and also factored and unfactored type. It's indicating the strength check and the service check. And also, if you want to define your moving load, you can do so right within the same interface here. And then following this, the top portion, you're gonna see the dead load components. And if you want to consider each load type, simply you can check on those options, and then make sure the weight density and the loading data are inputted correctly. So when the model is generated, the loading is applied according to this dead load weight information. And underground water, the ground level, how higher is it from the structure, the barrier, what is the self-weight of the barrier, and so on. And then going down, you could also define the system temperature and the temperature gradient load. And any type of loading that you need to reflect but don't really see over here, you can always complete modeling using the wizard and add an additional information outside of wizard. So if you don't see any specific data that you really need, you always have the flexibility to add an additional outside of wizard. And Midas wizards, they're not actually in the linear formatting, meaning you don't have to continuously click next to actually input the next set of data. You can actually jump around between many different tabs and all different input cells. So that way it's easier for you to overview exactly what type of modeling information you're inputting. And once you're done, hit OK. And before I hit OK, I'd like to mention one more thing. All of the wizard data, so let's say now I completed entering a set of data for the box culvert structure. You can actually save this data into a folder that you want to keep this data from. And later on, let's say the next day you found something that you need to modify. You can always come back to the program, open the wizard, and open the wizard file that you have saved previously. So this way, the wizard file can actually be saved, so you don't have to enter the same set of data once again. And once you're done, say OK here. OK. So non-skewed, straight box culvert structure has been modeled. Let me quickly turn off the node display. Okay. And when we go to the Workstream menu, you're going to notice that before we didn't have any data under the Workstream menu except the one material, right? But now we actually have a lot more data registered under the Workstream. And then in order to review what type of data the wizard has created, what you can do is go down the Workstream menu one by one. So it's going to be the same for any other type of structure or any other type of application in Civil. Whatever the case be, if you need to do some checking, you can go through the Workstream menu one by one and identify more easily. So going down, I have total 6 plate element types. 3.3 feet near the barrier, at the barrier. 2.8 and the regular 3.3 feet thick on the wall and the slab. And the bottom portion has 4.5 thickness, 2.5 and 1.5 for the wing walls. Going into the boundaries, this is where you can tell how the program reflects the soil surrounding the structure. So when you go to the point and spring supports, you're going to notice there are a set of data applied to the structure. And this type of linear fixity has been applied to reflect the soil. When you actually right-click on the linear and go to the table, you can actually see what is the spring data exactly that the program has converted based on your modulus soil information provided. And then also the links are created. So in the property of the link, you can also right click and review in the table what type of link is it. It's a general type that you can actually enter the stiffness in all DOF, and you will see the values for the stiffness value for every single link varies depending on the location of the link under the slab. And also the supports at the bottom of the link. So the link is reflecting the soil between the bottom slab and the fixed support. And then finally, at the 3 feet away from the slab, you're going to see these fixed supports are applied. The loadings are also created according to the loading data we've inputted. So when you go down, you'll be able to see different type of load cases the program has generated. And also when you go to the result and load combination, you will also notice a set of the load combination the program has generated based on the loading setup that you have defined. So basically all these actions are done using the wizard, and I would like to show you very quickly how you can actually do the same for other type of reinforced concrete structures. So quickly I came to the left side of the program and undid all of my actions, leaving just defining material portion. So now from a lot of data to nothing, I could quickly undo all my actions. And here, before I had a box culvert structure. But let's say this time I'd like to show you how you could do the normal type. Basically the same, just ensure some of the informations are, exactly what you needed. Say OK. So pretty much from the data that you enter from the wizard, the program will be creating the model for you. And same goes for the two-dimensional type 2. Just check on the two-dimensional. The portions that are unnecessary for two-dimensional modeling will be grayed out, and the wing wall portion will not be reflected in the two-dimensional modeling approach. And when you go to the transverse 2, these portions are grayed out. And then you can say OK to create the simple frames for the 2D output and design check. OK. So that's about the wizard modeling. And now back to the PowerPoint. I would like to now show you, so if the wizard is the fixed template that you have, there it will be very inconvenient. There must be some of the loadings or other type of circumstance that you need to reflect in your model. And those things can be handled by doing the manual modeling or modification. So first, if you want to model your culvert or frame structure, you could use the wizard. So that's the first approach that I've showed before. And second, you can actually import your CAD drawing. So regardless you're using AutoCAD program or MicroStation, it doesn't matter. As long as you save it into the DXF format, you could easily import it into Civil. And once you import it, that's just a bunch of lines and the elements and nodes. And from that point on, if you need to create 3D model, if you actually need to mesh it or manually create plate element one by one, whatever the case be, you can actually handle that using the node and element function in our program. And I'll be showing this number 2, importing the CAD approach, and also how you could utilize the node and element functions to mesh your imported CAD drawing. So as you can see from my screen, I just laid out my box frame structure. It's just simple lines. As you can see, It's just a bunch of lines representing the outline of the structure. And what I did, I actually saved it as a DXF format, so it can be imported into Civil. And in Midas Civil, when you go to the top left corner, oops, excuse me, you're going to find the import portion. And here you could actually import other bunch of programs, but the most useful, the AutoCAD DXF file import, is also here. So when you click it, you will be able to browse and find the DXF file that you have saved in your computer. So now I'm going to locate them. And depending on the structure complexity, if you actually want to import different parts at different times, you could actually put the lines in different layers in the CAD program. And when you bring it, as you can see over here, you can actually import layers separately or just one by one. And the reason why this can be very beneficial, not really for this type of structure, but it's for, let's say, the composite girder type of structure. You can actually import the girder lines separately, bracing separately, so that way you can actually specify the section for each different portion. But this time it's not the case. It's going to be, it's a monolithic structure and there isn't much variation. So I'm going to import all of them all together. And here I'm going to define the properties and just the thickness value. Say OK. So like this, I was able to bring the CAD drawing, the lines. And then from this point on, I'll be showing you how you can use the node and element functions to actually mesh this structure. So these lines, I imported from the CAD, but you could actually do the same thing using our node and element functions. So create the node, specify the coordinate that you want to create the nodes, and also using create element, you could actually define the elements, the lines that are, the portion that are represented with the line here. Let me quickly turn on the node. Okay. And from this point on, in order to make a model looking like this, let's say, I actually need to mesh the model that I have. So for that portion, I'm going to go to the node and element main menu, come to the element section, and then find a bunch of the mesh functions. And the mesh is actually plate element, so you'll be able to find them under the element section. I click the auto mesh. So if you want to kind of mesh, like carefully plot how to mesh mesh the portion, you can use the map mesh. But since for the convenience, auto mesh really helps you to actually do the meshing portion automatically. And here I'm going to say the method will be using planar elements. And you can actually choose the type, quadrilateral, quad, and also the triangle type, and just the triangle type. You have a choice. And let me actually go to the top view to select different plane one by one. So now I'm going to choose the wing walls. And using the dynamic control key over here, I'm able to select the wing walls just by drawing the window at the top. And here I could simply say, and mesh size can be controlled over here. I'm going to say, I want to say my mesh size to be approximately 3 feet, and you can say apply. And the same way, I'm going to repeat this process. Go to the top, draw the window, select this portion, and apply. And also, I'm going to choose the wall this time by going to the top view and say apply. I have to do one by one because these two portions are not in the same plane. And this message window is actually telling me that the selected line elements for generating mesh do not lie on the same plane. So I actually had to do them one by one. So just like this, if you get into any error, the program will let you know through the message window. So if something doesn't seem to be working, keep that in your mind and continuously check the message window. And let me speed up a little bit for the rest portions. I'm going to repeat what I did for the rest part of the wall and also now the top slab. So this way, you could actually manually mesh using the Node and Element main menu and the mesh functions that Midas Civil has. Okay. Now back to the PowerPoint. So this time I'll be covering how you can actually manually model the wing wall and modify them. So modeling portion, I think I covered it pretty much. In the wizard, you could actually just specify the dimension for the wing wall, and also you can use the auto mesh that I just showed like a minute ago to actually manually mesh based on the element that you have drawn or imported from the CAD. And the second one portion is, what if the wing wall isn't perfectly perpendicular, which is the way the wizard kind of creates the model for you? What if the wing walls are not perfectly at an angle? What if there's if it's at like a skew to the structure? That was actually that's also another commonly asked question. And for that portion too, I'll be also showing you in the program demonstrating. So back to the program once again. So all of those type of actions, rotating or putting, like changing the location of the actual physical shape of the bridge, those are all handled using our Node and Element menu. So anything related to changing the shape of your model will be in.
그런 예제가 오잖아요. 그대로 여기 많이 없잖아요. 여기 노르사에 들어와서 이주관이 들어가서.
Oh, I apologize. I think someone was muted. Okay. And from here, you can actually go to rotate for assigning the skew angle to the wing wall. So coming to the main menu, Node and Element, and rotate, I can choose the wing wall portion that I need to rotate. And then notice the tray menu has changed to the Node and Element function. And from this point on, I'm going to choose move mode because I'm not copying it. I'm trying to move it. I'm trying to rotate it. And the angle of rotation, let's assume it's going to be 20-degree outward. And it will be about x-axis since our x-axis and y-axis are laid this way. And the reference point will be right over here. And as I apply, as you can see, the wing wall has been tilted. And the nodes actually didn't follow along, so I'm going to choose this too. Go to node and rotate the same actions. Move, angle of rotation will be the same, 20. And about the z-axis and apply. So this way I completed rotating the wing wall. And the same procedure can be taken for the rest of them. To kind of show you real quickly. And also, just by using the node and rotate, you can actually do the same type of actions I did, moving the entire node and element all together. And I need to change the first point here. Okay. So this is how you can control the wing walls that are not at right angle. So the wizard will be creating the models with wing walls at right angle. But if that is not really the case you can always use our node and element functions. And this time, I want to cover how you can manually modify and model the top arch portion of the frame or the culvert structures. So let's say the top slab is arched. The wizard will be creating the top arch flat. It's not going to consider the arch for the top slab, but if that's the case you need, as mentioned before, you have the flexibility to do so outside the wizard. Okay. For this, I'm going to create, really quickly, I'm going to create a very simple model. Actually, I'll leave it as it is. So let's say from this structure, we want to reflect the top curve for the slab. What you can do is you can actually go to Structure main menu, go to the base structures, and find a bunch of the basic wizards. So Structure main menu, base structures, and arch. And let me actually open up a query dialog box. Go to query main menu and query nodes and measure the span information, which needs to go in right here. And by clicking two different nodes, I'm able to have the program, the program is computing the distance between the 2 points that I just selected. So this dialog box can be found under query and query nodes or query element. The number of segment right now, I have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I'm going to change the number of segment to 20. And the span information, as we found out using the query dialog box, is 60 feet. So I reflect that under the span information. And the height, let's assume it's a very slight curve of about 15 feet, let's say. I'm going to choose the same concrete material and section. I'm not going to assign anything, so let me give it a blank section data. It's okay. We are only trying to lay out the arch so that we can actually modify what we have already. And insert it about this point right here. Okay. So this way, using the arch wizard, I was able to create the arch that's right above the top portion of the top slab. And what we can do now is you can actually go to the node and element menu. And this time, what you can do is you can go to translate node and actually move these node locations in the vertical direction to match with the location of the arc. So for these two sets of nodes, this structure example is symmetrical, so they can be elevated by the same length. So I'm going to find out how far off they are in Z direction by using the same query dialog box. And the program is telling me it's 2.85 feet apart from each other. So I'm going to elevate the sets of nodes over here by that distance. So if you look at it right now, it looks very odd. But do you see? Do you get what I'm doing and where I'm getting it? So repeating the same, I'm going to choose the second set of node. Find out the elevation difference between the two, 5.4. and apply, doing the same action. And as you repeat this process and up to the middle portion, you'll be able to completely move your top slab to match with the arc that you created. And by doing this, I was able to create, I'm not going to complete all the actions, but I think you get the flow. By taking those actions, I was able to complete this model for this arc box culvert structure. So by using the wizard, like freely using the wizard and using the node and element function, you could actually complete modeling any type of culvert or frame or the pie frame structure here. Okay, now moving on to the analysis portion. So the first portion that I want to cover about reviewing the analysis is just using the regular diagram and tables. And let me show you that in the program too. For a 3D model like this, and I mean even for the 2D, you can always go to Result and find the bunch of the basic diagram and table results over here. And if you're new to Civil, you can go to Analysis and perform the analysis. I've already done it for to save time today. But if you didn't run the analysis, you can go to Analysis and perform analysis. Coming to the result main menu, this one on the very left side is where you're going to find all the basic diagrams and the tables. And I'm going to show you a couple examples. So forces, and as you know, this is a 3D model. So I do not have any truss element or beam element. I have everything is made of plate elements. So I can go to plate force moments, and here I can choose the type of force that I want to review about. Also, if you want to see a summary of the diagram, you can click on the red legend and say apply. And of course, I forgot this portion, but you can choose which load case and load combination you want to review the result for. So let me show you the first strength limits check load combination. And here we go. So this is a basic way to do. And also, if you want to the stress format, you can go to stresses, repeat what I just did by going to plane stress, plate stresses. And if you want to get to the table data, you can always click the shortcut right here. So for each diagram that you're reviewing, you can get to the table shortcut by clicking dot dot dot. But the main menu for the tables can be found on the right side. Result tables, and go to plate, and go to force, stress, or whatever that you need to review about. And you can actually filter about which location you want to review. So if you want, you can actually group like wing wall portion, slab portion, top slab, bottom slab. You can actually group them into different structure group. But right now, let's review for all of them. And you can check which load case or load combination that you want to check about and say OK. So this way, you can review in the tabular format too. Same goes for the stress. Come to plate, stress, select the load case, and say OK. And for the 2D frame model 2, you can do the same. When you go to the results main menu and find a bunch of the basic results, for example, forces, once again, and you can choose the load case just like before. Choose the force component that you want to review about and apply. And if you actually want to examine the structure more thoroughly, you can check on the value and apply. You can also zoom in to see more detail. And of course, you can go to the result table and find the beam, forces, and extract the output in tabular format. So that's about the basic way of reviewing the output. But as a second portion, what I want to cover is, before I go back to the presentation and kind of give you a brief overview, notice how when you review for the plate model, there are a lot more force and moment components than the conventional 2D bending moment that we are more familiar with. And for the end force data and the moment data for your design check, you always need the force and moment values in the 6th degree of freedom that we always use. So that portion I would like to cover separated. So reviewing the 3D result in the 2D envelope diagram is what I want to kind of address from this point on. So in the 3D modeling approach, it's difficult to obtain the final force and moment that you need for the final design check. So the play moment results, they need to be converted into the beam unit. And for the 3D model, it should be calculated as shown below. However, usually if you do the 3D modeling approach, you kind of have to do this portion on your own, one by one, about each segment. But we actually have several features that can internally perform such conversion calculation. They are such as plane cutting diagram, local force direction sum, and resultant force review. So coming back to our 3D model, here we go. Let's see what are those. So when you go to forces, the top 4 of them are the conventional ones: truss force, beam diagram, and plate force and moment that we just reviewed, right? But the 4th one is the plate cutting line diagram. So this one will actually present you the envelope moment diagram for the the plane that you cut. So right now I actually have 3 planes predefined. And let me actually walk you through how to do them one by one. But before I do so, let me quickly show you what the result will be actually presenting as an end result. So as you can see, before we were only able to review in the contour format. But if you define which plane you want to kind of cut through and see the envelope moment diagram or the shear diagram and so on, you can actually review in different format too. And let me show you how you can define one by one. So right now I have the depth plane for along the wall, width plane along the here, and length plane along the length of the bridge. And let me actually activate a portion of the structure so I can actually show you how to define them. But bottom point, how you define them, you just took out 3 points that define the plane. So that's really the bottom point of it. But let me demonstrate how to do one by one. So let's say, oops. Okay. Let's define name as longitudinal. And in the longitudinal direction, the bottom point over here toward the bottom portion is most likely to have the most critical result. So I'm going to draw the line along the very bottom. And then I'm going to say add. And I'm also going to draw vertical plane. And I'm going to locate the vertical plane. Okay. And let me click and say that I want to review about them. So this way, I could define my plane just by pinpointing 3 locations along the plane and have the program cut the plane and generate the envelope diagram for you. And also do the graphical presentation by checking on this option right over here. Okay, that's the first portion. And the other portion is about the local direction for sum. So let me activate the view once again and refresh, start my view. So this local direction for sum is a tool that actually calculates the result from the beam and or plate element that you choose and actually present you the final force and the moment. So let me actually activate a part once again. Using the window selection tool and hitting F2 key or coming to here, find the active icon. And here I'm going to use line mode. You can actually choose the mode, whether to draw a line and include any element that's along the line, or drawing a polygon. And if you have to use the polygon selection in order to convert the solid data. But we don't have the solid data, so I'm going to stay with the line selection. And you can choose the load case or the combination that you want to review about. And for the coordinate input, let me go over one by one. So along the bridge, in the transverse direction. Once again, let me refresh. So this way you can draw the line and have the program calculate. So the line that we drew is along the plate element. So as we went over just before, the plate force and the moment have more degrees of freedom. And the values cannot be simply presented into the final force and moment in the beam unit. But by using this local direction for sum, the program actually provides you the maximum moment shear in the beam force and moment unit. And you can also save this transverse and edit. And if you want to do the same for the wall portion, just draw another line, calculate it, vertical. Once again, this time, if you're interested in seeing the longitudinal results, here we go. And about the force, coordinate, as you can tell, as I draw the line, the local direction, the element local for that line, the program actually detects the local direction. So this is how you can control which direction for the plane, the line that you're cutting through. So these are the features that actually envelopes the result into the final force and moment format. And one last portion that was mentioned in the program, but something that I'm not going to cover today, is the resultant force diagram portion. And that function is more useful for, let's say, a composite structure that is built with plate elements. So when you first open the program, if you have an access to the internet, it's going to show you what are the new features that are implemented back in January 2015. And one of the features that was newly implemented is reviewing the diagram and the table for combinations of plate and beam elements. So when you click that icon, you're going to see more details about it. And this is something that's more useful for like a girder type of bridges, not really for the Culvert bridge. So I'm not going to cover this portion, but feel free to take a look into the details and learn how to utilize this tool too. Okay, the final portion is about the design. And the design actually can be done in the 2D format. In MIDAS, there are two types of design. You can do design checking and actual design. And for the reinforced concrete structure, you could do the beam design and checking, and column design and checking. For the design, you can provide a rebar requirement. I mean, that's what the design does for you. And the checking will be letting you know the strength and the section cracking check. Oops. We are not done yet. So as mentioned before, I came back to my 2D frame model for the box type of structure. And let's take a look at the model and the design steps one by one. So if you want to do the design or load rating for the culvert or frame type of structure, you have two options. One, you could actually take the simplified approach in 2D and do the automatic design and load rating check. And second approach is by modeling the entire thing in 3D view and actually just extract your final force and moment and utilize those to do the design check or optimization within your spreadsheet. So you have two different approaches, actually doing all the way up to design within the program using the 2D modeling approach, or versus if you need to extract more accurate output, you can actually model the structure in the full 3D view, and just the final step that you can do will be extracting the final forces and moment. So that's the two available approaches for this type of monolithic reinforced concrete structures. So if you were to do the design manually from the 3D model, you can actually go to the result main tab, go to force, review the diagram, or review the table as I walked over just before. And now from this point on, I will be showing you briefly how you can actually go to the design check for the 2D beam model. So this model, unlike the one that we've been kind of playing around with, this is very simple. As you can tell from the work tree, all the components are made of beam elements, making the model 2D completely. And I actually have different sections for the parts that, like different design check needs to be done. So the wizard will actually create a model considering this. So for each section, this is because the rebar data and the design data are entered for different sections. And so segmenting the sections into for the identical sections, but segmenting the actual property is because it's to enable you to do the separate design check for each portion. And all the design can be found under the design main menu. Today I will not be going over the steel design or composite design. For our structural application, RC design is what we focus on. And actually, design portion is very simple in our program. So Since you do a lot of work in the modeling portion already, defining your structure, what it looks like, and actual loadings, and defining the boundary conditions. So basic physical conditions are all already there from the modeling portion. And what you do in the design portion is ensuring, letting the program know what code you're using, what are the factors that you're using according to the code, and a couple more data that are required for the design, and the rebar data. So I'm going to show you one thorough example. So choosing H2LRFD12 as my design code, I can go to the design code. A lot of older codes are also available for reinforced concrete and steel design check. And for steel and RC design check and checking, both are available. So design code, H2LRFD12, and you can actually specify the moment distribution factor for beam according to H2. Strength reduction factors, you can update it by the code. If your state has any like difference between H2LRFD, you can reflect that by manually modifying here. Modify the concrete material. So I have two different materials defined. They are actually the identical materials, but I actually just specified, so these locations where the color of this segment is green, that's where I'm really concerned about. That's where I need to do the design check. So I actually just create an identical element just for the presentation purpose, for the demonstration today, because if they are all in gray color, I just wanted to indicate this is the location where I'm concerned for the design check. So I separated the color just by defining an identical material, but assigning different color for the material. And assigning different color and all those things, you can control that under using going to this TV icon and associated with the setting symbol. So right over here, this is where you control how to assign different color for different part of the model and so on. Okay, so grade C 4500, what you have to do in the modify concrete material window is to ensure the rebar data. And also, if you need to change the specified compressive strength or any other information, you can actually change your code to none. And when you do this, what will happen is it's going to open these parameter cells for you to manually modify them. I'm going to stay with what we defined as originally and modify. Limiting maximum rebar ratio. Scale up factor for the columns if you want to do so. You can choose the column portion, which is the vertical members. And apply the factor. So you can actually enter the rebar for two different types, design and checking. And design will be letting you know the rebar information, and checking will be letting you know the actual strength and the crack section check. And design rebars are relatively simpler. As you can tell, you simply input the stirrup data and any torsional reinforcement rebar data. I've actually done so for the critical locations I want to check the design for. So remember, turning back, showing the display. So remember these portions, they actually have different sections applied to. So let me open the query and query node elements. And I'm going to select one by one. This portion, right? And this portion, and this portion. And when you actually check in the message window, you'll be able to see different sections applied to them. Element 1, section 1. Element 7, section 7. Element 16, property 16. And this type of summary data about an element, I extracted by going to the query main menu, query elements, and query dialog box. Okay. So beam section data for design, I've actually done them for the beams. And also for the column data, I've registered, actually did them for this one. And you can actually enter the rebar data for the column design using the column section data for design. Okay. And then you can do concrete code design. So you've already entered all the data that was needed. And then now you can go to beam design. But before we go, so concrete design table is a table that will show you a summary of the design inputs that you have entered. But besides the scale-up vector for the column and the rebar data, things can be, it's just about the vectors. So we only have one table for RC design. Concrete code design, and you can go to beam design check, have the program do this iteration. And actually about every single section, you can check the result. This is a summary data. And when you check on each them, you can actually generate the graphical result. Let me repeat the process. So you can review the summary data from the table. And okay, RC design, finally concrete code design, and beam design here. And the program will be providing you a summary of the design check result. Check on the options that you want to review more thoroughly about, and click either graphic or summary. And it's going to show you the design check summary graphical format. And I selected two different locations, and I can review both locations just by going back and forth in, between number 1 and number 2. You can print them. You can also save it into an image file. You can also extract the summary data in the text format. You can save it too. And also about each element, you can actually extract the detail report too in the text format. All of these materials will be uploaded into our website, as I went over for how we uploaded on the steel materials. So feel free to go through each report one by one. Okay, so that was about, and then you can also connect the result to the model view here. So that was about our RC frame and culvert type of structure application. So today's session has, it's finished. I covered the parts that I wanted to cover. Let me go over the questions that are submitted. We ended earlier than planned, so I'll take some time covering the Q&A sessions. Couple questions. What is the recommended size of plate element? So the plate element size can vary. What I normally do when I actually need to take out the do the full case study, I actually generate the same model using different size of plate element. And when I actually test out some of the result, and if the plate size is good enough to kind of make the result stable from that point on, I stay with that element size. So let's say I'm trying to evaluate plate element size 1 feet, 2 feet, and 3 feet, right? Between the model that has 3 feet plate size and the 2 feet plate size, the results may vary. But between the models that have 2 feet size of plate element and 1 feet size of plate element, the result may not vary as much. So when I start seeing the difference reduced, that's when I actually stay with that element size. So that's another benefit of using the wizard. You don't have to continuously resize your mesh. You can actually use the mesh element input portion to control how you want to model the structure. And all of the questions that I go over right now, I will be also providing a summary of the Q&A after, when I upload all the materials. So yeah, you should be able to check them after the session too. I might not be able to cover all of them for the sake of time. There's a lot of questions entered in, but if anything has been remained unanswered, I will be contacting you individually and also kind of publish the Q&A from the session when I upload it onto our website. And for the soil reflection, so in the wizard that I created, based on the property that I input, the soil soil spring type has been all linear. But you can actually change some of the parameters, and also outside of wizard, you can actually model the nonlinear springs and compression or tension-only springs. That portion actually comes when I call more into the soil structure interaction session. Keeping this question in mind, I'll try to cover that portion in more detail too. So the vertical members, it's not actually, it was elastic links that was used to model reflect the bottom soil, and that was only in the vertical direction, in the compression only. And then based on the link, the fixed support has been applied at the bottom. But you can actually, it's a portion of the wizard where you could actually specify if you want to apply soil spring support or fixed support. And for that model, I actually created fixed support, but you can actually specify spring support options and have that taken care of. Horizontal springs can be generated, yes, using our integral bridge feature. So basically in our program, you can actually find a portion called, let me actually take you back to the program. There is a feature called integral bridge. And here for the abutment portion, you can actually use this function to automatically apply the compression only soil spring property. And for this portion, it covers some step-by-step process. So I will share a tutorial manual that thoroughly covers step-by-step process. But basically, if you look at the interface, you'll be able to tell the information that are required. You can actually input, like the spring data, the type of the spring and also the stiffness for the type. But what you can do in our program using the integral bridge feature, you can actually put in the geometric data, soil parameter, and have the program automatically create the model for you. And as an example, here I have an integral model. And as you can tell, I have an abutment wall. And here I used this integral bridge feature to generate all sets of spring data, linear spring, compression or tension only, or multilinear. Different type of soil springs are applied to different type of different portions of the substructure. Let me open the tree menu and show you one by one. So the linear springs are applied for the vertical on the pile. And how can I tell the components are applied in the vertical direction? If you look at the symbol, it's a hexagon symbol, and it's made of 6 triangles. Each triangle going from the noon direction, from the north going clockwise. Each triangle represents the x, dy, dz, rx, ry, and rz. And there's a yellow color triangle in the dz direction, meaning this linear type of spring data is applied for the vertical on the pile. Compression or tension before getting to that portion, multilinear springs are applied for the lateral on the pile. So this is the nonlinear spring applied for the pile. And the compression only springs are applied onto the wall about the lateral direction, as you can tell from the 2 triangles going from the north direction. And when you actually open the tabular format of the data, you'll be able to see that it's not just the symbols, it's not just a simple data. You can actually check what are the details that the program has produced based on the basic data that you entered in the integral bridge function. So depending on the type, let me turn off some of the windows, so maximizing our tabular view. So this way, for each spring data, you'll be able to check how are the different data set. And for the multilinear portion, it cannot be defined with just a simple stiffness value. So moving on to the back, you will be able to see how the nonlinear the function has been graphed for the multilinear type of spring. So that's how you can actually handle further about our the lateral direction springs. Okay.